Good day, sir. Good day to everyone. My name is Olegario,
And I'm Sir Jausan.
and we will be the representative for our group and to discuss and introduce you another algorithm called the Bellman-Ford's algorithm.
The Bellman-Ford algorithm solves the single shortest path problem when the edge weight can be negative but not when it cannot be negative. And when some of the edges of the directed graph have energetic weight, this algorithm works correctly. When there are no negative weight cycles, we can determine the shortest path between source and the destination. Bellman-Ford algorithm detects and reports the presence of negative cycles in a graph. Based on the principle of relaxation, more accurate rules gradually recovered an approximation to the proper distance until finally reaching the optimum solution. Bellman-Ford's algorithm and Dijkstra's algorithm both are single-source shortest path algorithm, i.e. both determines the shortest distance of each vertex of a graph from a single-source vertex. However, there are some key differences between these two. So we follow the dynamic programming approach in Bellman-Ford's algorithm and greedy approach in Dijkstra's algorithm. Let's see the other major differences between these two algorithms. Bellman-Ford's algorithm works when there is a negative weight edge. It also detects the negative weight cycle, while the Dijkstra's algorithm may or may not work when there is a negative weight edge. However, it will definitely not work when there is a negative weight cycle. The Bellman-Ford's algorithm when the results contain the vertices which contains the information about the other vertices they are connected to, while the Dijkstra's algorithm the results contains the vertices containing the whole information about the network, not only the vertices they are connected to. As for the Bellman-Ford's algorithm, it can easily implemented in a distributed way, while the latter, it cannot be implemented in a easily way as same as the Bellman-Ford's algorithm. Bellman-Ford's algorithm it is more time consuming than the Dijkstra's algorithm, while the Dijkstra's algorithm it is less time consuming. Again, as we've mentioned before, Bellman-Ford's algorithm is a dynamic programming approach taken to implement the algorithm, while the Dijkstra's algorithm has a greedy approach and it is taken to implement this algorithm. Another difference between these two techniques, we have the Bellman-Ford's algorithm have more overheads and less scalability than the Dijkstra's algorithm, while the latter, Dijkstra's algorithm, have less overheads and more scalability than the Bellman-Ford's algorithm.
So there are four steps in finding the shortest path using the Bellman-Ford's algorithm. So first is to get the source vertex. So here we have the following graph. So let's say I want the source vertex to be vertex A. Now we have to set the distance of vertex A to 0. Next is to set the rest of the vertices to infinity. So here we have vertex A has the distance of vertex A to 0. Now we will set the distances of the rest of the vertices to infinity. So we have to write all of them as infinity, infinity, infinity. Now we have listed the distances of each vertex. Now let's list all the edges and the vertices of this graph. Now listing the edges is so we will find the pair of vertices which their edges. So let's say AB. The order of the vertices here is important because it is A to B. So it has to be A to B and not B to A because that's different. So A to B and then next is A to E. Then B to D. Now we have listed all 1, 2, 3, 4, 5, 6, 7, 8, 9. We have listed all 9 edges of this graph and also the vertices. So there we have 7 vertices. A, B, C, D, E, F, G. And now let us move on to the last step, which is relaxation n minus 1 times. Now you may wonder, what does relaxation mean? So let me show you a little demonstration. Relaxation is simply the process of finding the distance of a vertex. So for example, we have the vertex E. So for example, we set the distance of vertex E to 7. Then we set the vertex of its neighboring vertex, let's say A. We set the distance of vertex A to, let's say, 6. So let's say distance of A is 6. Distance of E is 7. Okay. Or maybe we just set this to 3. 3 lang. Then the distance of the edge A to E, let's say, is 2. So yeah. So in order to relax this vertex, we will find the sum of the vertex that is being pointed to. So let's say the distance of vertex A and the distance of the edge A to E. So let's say D of A plus C of E equals let's say less than distance of E. So for example, 3. The distance of A is 3, and the distance of the edge is 2, which is less than 3. The distance of E is 7. So 3 plus 2 is 5. So the new distance, the sum of these 2 is 5. So it is less than 7. So if it is less than 7, then you have to change the distance of E, which is now 5. Now, so that's the process of relaxation. We shorten the distances of each vertices in order to make the shortest path possible. Now we know what relaxation means. So let's start. So let's say we listed all the vertices here and all the vertices here and all the edges here, which are 1, 2, 3, 4, 5, 6 iterations. Since we have to do relaxation 6 times, which is n minus 1, since these are 7 vertices, so 7 minus 1 is 6. So now let's start doing this. So let's say we'll start with the vertex A. So first is the AB edge. So A to B, 0 plus 2. 0 plus 2 is 2. So this is infinity. So we simply change infinity to 2. Then next is A to E. A to E is 0 plus 3 is 3. So we need to change infinity to 3. Since 3 is less than infinity. Next is B to D. B to D, 2 minus 4 is negative 2. We change that infinity. Next is D to E. D to E, negative 2 plus negative 3, negative 5. So let's change this once again. Negative 5. The next is B to C. 2 plus 1 is 3. So let's change infinity to 3. The next is D to G. So D to G is negative 2 plus 7 is positive 5. So positive 5 in G. Next is G to C. G to C is 5 minus 2. 5 minus 2 is 3. So it's already negative 3. It's already 3, so no change. And lastly, 5 plus 2. So 5 plus 2, 7. So 7, change that to 7. And then that's it. So we basically change all of the infinity values into their own shortest value. So that is the first iteration. So let's just list down all the distances here. So A is 0, B is 2, C is 3, D is negative 2, E is positive 5, F is 7, and G is 5. Now we are finished with the first relaxation. Now let's move on to the second time of relaxation. So let's do this one more time until we get the shortest vertex. So let's do this again. A to B, 0 plus 2 is 2, so no change. Next is A to E, 0 plus 3, 0 plus 3 is 3. And negative 5 is still less than 3, so no change. Then next is B to C, 2 plus 1 is 3. So it's already 3, so no change. The next is 2 minus 4. 2 minus 4, negative 2, already there, no change. The next is D to G. Negative 2 plus 7 is positive 5. It's already 5, so no change. Then next is G to C. G to C, 5 minus 2 plus 3. So no change. Then next is 5 to G to F. 5 plus 2, 7. So no change. Then next is E to F. Negative 5 plus 5. Negative 5 plus 5 is 0. Since 0 is less than 7, so we need to change that. And that's for the second iteration of relaxation. So we mark the new values here. 2, C is 3, D is negative 2, E is 5, wait, that's negative 5. Then F is 0, then G is 5. Now let's move on to the third iteration. We will do it again. So A to B, 0 plus 2, 2, already there, no change. A to E, 0 plus 3, negative 5, no change. B to D, 2 minus 4, negative 2, no change. 2 plus 1, 3, no change. Then D to G, negative 2 plus 7, 5, no change. G to C, 5 minus 2, 3, no change. 5 to 2, 5 plus 2, 7, 0 is already there, so 0 is better. Then E to F is negative 5 plus 5, 0, then no change. So we are at the same correct answer. If we did arrive at the same correct answer, then we can say that we have found the shortest path of each vertex using Bellman-Ford's algorithm. So if you did the relaxation 6 times or less and you come up with the correct answer, then you can say that these are the correct answer for this graph. So there you have it.
Now let's look at its pros and cons. The pros of Bellman-Ford is that it accepts negative weighted values, unlike Dijkstra's algorithm. For graphs that contain negative edge values, arriving at the accurate shortest path using Dijkstra's algorithm doesn't work, so the Bellman-Ford algorithm is being used instead. The cons, however, has something to do with the negative values. So let's say we have a simple 4-vertex graph here. To get the shortest path, we need to relax all of these edges 3 times. Setting the vertex A as the source vertex and the rest of the vertices to infinity, we mark A's distance as 0. Then we go on and relax each vertex using each edge. As you can see, we relax all of the edges less than 3 times. Now let's change this graph by drawing another edge like so. 5 edges total. So we need to relax these edges 3 times or less, just like before. Let's start with the same source vertex. We have reached the n-1 limit of iterations. But do you think we can still relax this afterwards? Yes, but that's not how it's supposed to happen. We are supposed to stop relaxing this once we've reached the limit, but it still continues. The reason for this is because of a little occurrence in these vertices called a cycle. In this cycle, if the sum of the edges values results to negative, then the graph cannot be solved. So that is it for our presentation. Thank you for listening and have a good day.